So we have already finished the describing the backward pass just for this particular output layer. Means that this one is not just involved at the neuron 5 or node 5, it also can be generalized in neuron 6, okay, because it's still at the output layers, okay, because neuron 5 and 6 is at the output layer. So in other words, you can you can also repeat the same process there for the same process there to find W35, W the updater of W35, the updater of W46336, and the updater of your bias 6 at the neuron 5 using the same concept as this one, which is come from the examination of this neuron number 5. So it's the meanings that you can generalize in that way. Means that in order for you to find each and every parameter here involved in every neuron inside the output layer, then you can use this formula. Means that to find del E over del B, you just multiply between the delta of that neuron with multiply that delta with the input that going toward that line. Okay, if you talk about B5, this one multiply with this one. If you talk about WT5, this one multiply with this one to find the del E over del WT5. So you can repeat the same process for neuron number 6, which produce this expression as well. So now let's continue to the adjacent layer, which is the hidden layer. Okay, we already identify the updater of this one, this one, this one, this one, this one, and this one. Now we want to find the updater of the parameter. Doesn't matter is it W or B that involved in the the hidden layer, which consists of two neurons, which is neuron 3 and neuron 4. So again, let's consider or focus. We just focus first on finding the gradients or the updater of this W13. Consider W13 first. So again, we want to find the del E over del W13, which represent how much the change of W13 contribute to these total errors there. So that's why we need to find the gradient of this W13, which is also called as a del E over del W13. This one is a little bit complicated in terms of generating the expression still using the change rule, because now the change rule is a little bit long as compared to if you want to find the gradient or the gradient of every parameter that involved at the output layer, because here to relate between this W13 and E is a little bit long. You need to cross this output layer parameter first before you can arrive here. So it's the change rule. The change rules there is very long. So that is how we define that. Okay, how to define del E over del W13. Okay, it's expressed in this one. It's a little bit too long. So why is very too long? Because here you can see that from error there, because to find the error here, error function here, W13 is actually contribute towards into two direction. One is going to this W35 line, and another one W13 also contribute to this line, which is to W36 line there. Okay, 36 line and 35 line is affected with any changing happen at W13, which is why you can see that meanings that the errors there E is depends on E1 and E2, where E1 is depend on Y hit 1 and E2 is depend on Y hit 2. So means that to find the del of, or the gradient of this one, you need to consider both variables, both directions there, which, because this one contributes both direction, means that it also contribute towards this direction, it also contribute to that directions, means that you cannot cancel the W2 head like we do in the previous one when we try to count the gradient of W35, because this one only produce or contribute towards Y1 head, but this one it contribute both Y1 and Y2, which is why this expression is represent this green line at the upper there, and this expression is come from this direction. Okay, you can try to check my expression there. It should be similar there, means that Y, okay, del E over del Y head 1 means that come from that direction, and then you again you repeat the same process. This one is Y1 over net 5, and then because this is come from activation function of neuron 5, this one is come from input function of neuron 5, and then once you arrive here, then you can do del O3 over del net and del net over del, okay, this one is come from yeah, it come from this direction, means that this one is come from this point over here, and then this one is until you arrive at the 1 3. So, and these expressions there is represented by this the upper green lines there to express this component. So later you can try to check back that one. Okay, okay, there's some tips there if you not sure what happens, which one need to be which one. Okay, you can see that again, to express this one, you must make sure that you must start at E there, and you must stop at W13. Okay, and again, because why we have plus there, because we have we have a two backward pass involved in this one. There's a two backward pass mechanism, one from here, one from here. Okay, of course, that's why we still this second item there still have a start with E and end with W13. And then if you want, by focusing on this direction again, Y E is depends on Y1. Okay, Y1, so Y1 head, so that is common sense there. And then of course you need to repeat the same component here after you declare this denominator as y delta Y 1 head, then you need to write the numerator at the adjacent there should be the delta Y1 head. And then of course, I think this again you need to remind yourself, this one should divide into two things there. Okay, so again, this is I just neglected the O5 there. I just put it because O5 is equal to your Y1 head. So now you have here a activation function where the variable is net, and then this one is a linear function where the variable is the input variable for this function is your W. Okay, this one is W3. Of course, this is the W involved for including at this one as well as this one, which going to that direction. So, okay, so how do we know that this should be del net? Because you can see that for this one going into that direction is depend on this function where the input is net. Now the input is net, and at this neuron it should be net 5. Okay, so that's why it become del net 5, and then that's why it become net 5 over here. So now again you copy that one into upper into this numerators there, net 5. So how to know this one should be del O3? So if you go to the net 5 here, okay, net 5 there. So okay, this one is a little bit different from the previous one, because you want to pass back to, you want the flow going into that direction. You don't want to stop the expression there. If you remember, this input function have to instead of have consists of B5 and W35 and W45. W35 is actually must multiply with O3, I'm sorry, O3 there, and W45 here must multiply with O4. Okay, this is O4 and this is actually O3. So meaning that if you want to make sure that this expression still can be extend towards this direction, you must not do del net with respect to del W35, because that will stop your expression there. Means that that is in the case if you want to find the updater of this W35. That is what we do during the previous one, where we want to we want to find the parameter, the updater of parameter involved in output layers there. Okay, but to make sure that this error can be propagated towards the hidden layer, you must do the partial derivative of del net 5 over del O3. So it's not del, it should not be del W35, because if you do it with del T5, then you stop the change rule up into that stage only. So that's why it's you need to do in another way around, which is you need to derive with del O3 to make sure that, because O3 is come from this one. If you do with respect to W35, then you stop the change rules there. That's why you need to do with the derivative with respect to this one, because this one is come from this one. Now it will connected because the O3 will connected between this 3 and 5, not number 3 and not number 5. That's why at this component we must do that. Now then you can go continue your change rule with del O3 here, and then this del O3, of course, the O3 is related with this f activation function of this one, which is f, and the input of that function is net 3. So now you can derive from that del O3 over del net 3, and del net 3, which is here, and then you can close that, the change rule at here. You can stop here by derive with this del net 3 over the del W13. So that's how you can extend that. So you must it's a little bit different from the previous one. Instead of stop at here, if you want to stop here, if you stop here, that is related to the output layer only. So that's why if you want to extend the change rule going from this stage into this stage, then you must do the derivative of the del net 5 with respect to del O3, because that will extend the change rule going into this direction. Okay, so I think same with this component. You can see that here we use a del net 6, which is here. We don't do the derivative with respect to W36. We do with del O3, because we want to extend, because this is the only O3 is only the variable that could extend the change rule from here to here. Okay, so that's the reason. Or you must remember that, and seriously you must remember that, because that is the only way you don't have, then you don't have to memorize this thing. You know step by step from scratch, then you know how actually you can express between there's a difference between input layer and hidden layer. At the hidden layer, it's a little bit complicated in terms of to generate the change rule, because you need to extend one by one, and you must finish the extension there, the change rule there must finish with the W that you want. If you talk about W13, the denominator should be del13 and so on. Okay, so from this long expression there, I can factorize in this way, because this component, there's a same components in both items there. For the first item there, you have the same component as the second items there. Okay, so that's why I factorized it. I bring it out and make a bracket there. So now the one that should be have a different component is already inside this bracket.